Okay, so this is an overview of things to look out for when determining convergence and divergence in a series. And these are the 10 tests that you can use. And I'll go over a quick explanation of each one. So you could use the divergence test when it looks like the limit might approach zero, or it might not approach zero, sorry. And the ratio test if there's difficult terms that would be hard to deal with otherwise. The root test when there's an x to the n inside of the function, inside of the series. And the integral test when it seems like it'd be fairly easy to integrate. And as a side note, it had to be positive, continuous, and decreasing for the integral test to work. And for the direct comparison test, if you have something that's kind of giving you trouble, so if it's something that you could find convergence or divergence for otherwise, but there's like a +3, a constant, or another term in there, then you can compare it to another one to figure out divergence or convergence. And the limit comparison test is similar, except you're comparing the limits. The direct comparison test is a little bit easier to use, so this should be more of your go-to, but this sometimes works when the direct comparison test is not. And the alternating series test should only be used when you have a -1 to the n, because those are typically difficult to deal with. You can't really find like the limit, or you can't do a lot of other things. And for the geometric test, when it's a number to the power of n, then you can find convergence or divergence depending on whether this is greater than or less than 1. And for the p-series, if it's 1 over n to a number, you can find convergence or divergence depending on whether this number is greater than or less than 1. And telescoping, if the limit of this one is equal to 0, the first term and one term minus another one is 0, then it's convergent, and then you can find the sum by canceling out terms. So yeah. Okay, so this is a overview of sums and sum estimation remainders, and we can find the sums of geometric series and telescoping series. So for an infinite geometric series, you use the formula a over 1 minus r, and for a telescoping series, you can cancel out terms, and whatever left will be your sum. And then for estimating remainder, you can do it for alternating series and for integral tests, and it's here. The formula of the remainder is less than or greater or equal to, the absolute value of the remainder is less than or equal to a sub n plus 1. And for the integral test, 0 is less than the remainder, which is less than the integral from n to infinity of f of x dx. Okay, so this is the first problem in our numerical series worksheet. And it's the series from n equals 1 to infinity of 3 to the n minus 5 over 2 to the 3n plus 1. And the first thing you should do is recognize that that you can make this into a fraction to the power of n, which makes it easiest to use a geometric test, but there's other tests you can use, like the ratio test or the root test. In this example, we're going to use the geometric test. So the first thing you want to do is simplify it. So we're going to take this 3 to the -5 out, and this 2 to the first power out. And because this is 3 to the -5th power, you actually put it in the denominator, which might be a common mistake. And so then we have this constant, and then you can bring this 3 down, so then it becomes 8 to the n. So then you get this fraction 3 over 8 to the n power times the constant. And then it makes it easier if you make it to the n minus 1 power. So what you would do is you just take 3 over 8 out of this and multiply it into the constant. And then you get that r is equal to 3 over 8. And because 3 over 8 is less than 1, it's convergent by geometric test. And then to find the sum of a geometric series is a over 1 minus r. And if r is less than 1, if it's convergent, then you can use this. And so then we plug in the a, which is our constant, which we have here, over 1 minus r, which is our fraction, which we have here. And then you just simplify and you end up with 1 over 810. So yeah. So this is the second problem in our worksheet. The series starting at n equals 1 and to infinity. And it's -1 to the n times cosine of, in the numerator, 2n minus 52, and in the denominator, n to the 4/3. And here a common mistake would be to think that you cannot do the divergence test because of this -1 to the n. But you take the limit of the a sub n part, excluding the -1 to the n, and you can still do the divergence test. So the divergence test is kind of a go-to because the limit, taking the limit of any function is usually fairly easy, and if it does not equal 0, then you have your solution already. You don't really need to prove anything else. And so that's what we did here, is we took the limit of the function. And the limit of cosine of this inside thing, you can just take the limit of this inside and then evaluate cosine of that. So the limit of this inside, by dividing by an n, you get 2 minus 52 over n to the 1/3. And this 52 over n goes to 0. Then you just end up with the limit as n approaches infinity of 2 over n to the 1/3, which is equal to 0. So you end up with basically limit as n approaches infinity of cosine of 0, which is equal to 1. And 1 does not equal 0, so it's proved divergent by the divergence test, and you cannot find the sum for the divergence test for the series. So this is number 3 in our worksheet, the series from n equals 1 to infinity of 3 over n squared plus 3n plus 2. And because we can factor the denominator, we can use partial fraction decomposition to split it up into 2 terms. And using those 2 terms, we can do like a telescoping test. So first we factor the bottom and we get n plus 2 times n plus 1. And by putting an a and a b as like substitutes in the top, we can evaluate this. And so you get 3 equals a times n plus 1 plus b times n plus 2, which is just taking this since they have the same denominators. And then using that, you can simplify and you realize that b is equal to 3 and a is equal to -3. And so we can put the 3's on the top, and then you get one term minus another term, which means we can use telescoping series. And first we're going to take, telescoping series says that it's convergent if this first term, if the limit is equal to 0. And it is, because the bottom will grow much faster than, well, the top's not growing at all. And to find the sum, eventually we know that the terms will cancel out because of the minus sign. So we have this part, this 3 over 2, and the last part that both won't cancel. But because this n is kind of a substitute for infinity in this case, this is going to be essentially 0. And therefore we can say that the sum is just this 3 over 2. Okay, this is the 4th problem in our worksheet, and it's a series from n equals 2 to infinity of -5 to the 2n over n squared times 8n. And we're going to use the ratio test because the ratio test is fairly easy to use. It's pretty versatile. You can use it for a lot of different functions. So what we're going to do here is we're going to take the limit as n approaches infinity of a to the n plus 1 over a to the n. This function, right, this part of it being a to the n. And one thing that people might get confused about is this 2n here. Now, a lot of people might do 2n plus 1, but it's really 2n plus 2. And the reason why is because it's 2 times n here. So if we do 2 times in parentheses n plus 1, it ends up being 2n plus 2. So we're going to do that, and we end up with this right here. And a lot of these terms cancel out, like n plus 1 squared on the denominator and n squared in the top is going to go to 1 eventually. But in the case of ones like -5 to the 2n plus 2 over -5 to the 2n, you take the plus 2 out and you end up with 25 times these two that are exactly the same, and then they cancel out. And you can do the same thing for 8n plus 1 below 8n. So then you end up with limit as n approaches infinity of 25 over 8, and 25 over 8 is greater than 1, and therefore the series diverges by ratio test. This is number 5 in our worksheet, and it's a series starting from n equals 1 to infinity of -1 to the n on the numerator, and in the denominator, n times ln of n. And because you have this -1 to the n, it's easiest to use alternating series tests. So 2 things that need to be met for alternating series, the convergence to be proved, is that the series has to be decreasing, and the limit also has to be equal to 0. So here it says that it's decreasing, and also if the bigger one is smaller than the, like if the n plus 1, if the farther on the x-axis is smaller than the left side, then you know it's decreasing, it's going down. So, and the limit is equal to 0 because this bottom is growing and the top is just staying constant, so it's equal to 0. And so it's proved convergent by alternating series tests. And then also by P series, we know that n times ln of n is greater than n, and therefore because the denominator is larger than that of the harmonic series, we can conclude that the series is absolutely convergent. So yeah. So this is number 6 in our worksheet. worksheet the series from n equals 1 to infinity of 2n plus 1 factorial over n times e to the n squared. And we can use a ratio test for this. And the ratio test basically says that the limit as n approaches infinity of a sub n plus 1 over a sub n is less than 1, then it's convergent. And if it's greater than 1, it'll be divergent. And so we do that here. We take the limit and then we simplify it, like I explained how to simplify it in an earlier video. And we end up with 0. And because 0 is less than 1, it's proved convergent by the ratio test. And because the series has no negative term, the series must be absolutely convergent. Okay, so here we have a sequence and we have to turn it into a series. So the first step would be to recognize that it goes negative, positive, which means that there has to be a negative 1 to the n in it. And it's easy to get misled here because this negative 3 might make you think of a different pattern. It doesn't quite make sense with this. But really this is negative 6 over 2. And if we realize that this is negative 6 over 2, then if we divide all of them by 3, we get 2, 3, 4, 5. And because it's starting at 1, we know that this would be 3 times n plus 1. Then the bottom, if we take away 1 from each of them, we get 1, 4, 9, 16, which is a quadratic pattern. That's how we know it's n squared plus 1. And then if we take the limit of the newly found series, excluding the negative 1 to the n, then it's equal to 0, and it's decreasing because this n squared term will get bigger faster than the n term will. And so therefore it's convergent by alternating series test. But if we do comparison test for n over n squared, which is equal to 1 over n, then it's proven divergent because the one that's smaller than it, that's pushing it upwards, is divergent, and so all it can be is divergent. So it's conditionally convergent because we proved it to be both divergent by comparison test and convergent by alternating series test. Okay, so these are general errors for each of the 10 tests that are likely for people to make and things to watch out for. So for ratio test, different like categories of terms simplify differently. So factorials would simplify differently than like x to the 4th power when you take the like n plus 1, I mean n to the 4th power. And then you have to also remember that it's a sub n plus 1 over a sub n and not the other way around. And you have to remember that you're taking the absolute value. And then for the root test, you have to, and sometimes it's tricky if they look similar, but they all have to be in the same format, x to the n. And then for alternating series test, it must be decreasing and the limit must be equal to 0. And then if it's inconclusive, it does not prove divergence. And then it can only prove convergence. And then for the divergence test, it cannot prove convergence, it can only prove divergence. So if the limit is equal to 0, it's inconclusive. And then for the geometric test, some patterns are difficult to interpret. So this right here, 3 to the n minus 1 over 2 to the 2n plus 1, you have to get it down to just 3 over 2 to the nth power. So what you do is you'd first take away this part of it, and then this part of it, and then you'd square the 2. If you square the 2 first, it won't be correct. And then for the p-series test, do not confuse the pattern with geometric because it's reversed. So for p-series, if the p is less than or equal to 1, it's divergent, and if it's greater than 1, it's convergent, and it's opposite for geometric tests. And then for integral tests, it has to be continuous, positive, and decreasing before you take the integral. For telescoping, you cannot prove divergence, you can only prove convergence, so the limit has to be equal to 0 of that first term to prove convergence. And then for the direct comparison test, the one on the bottom, if the one on the bottom is divergent, it's pushing the other one up, and the other one must be divergent as well. If the one on the top is convergent, then it's pushing the one on the bottom down, and so the other one must be convergent. So don't get those confused. And then for the limit comparison test, it can only prove it's opposite from this one. It can only prove, or the same actually, it can only prove that they're both convergent or both divergent. So if you're comparing, if you know that b sub n is convergent, then you can only prove that a sub n is convergent as well. And that if b sub n is divergent, you can only prove that a sub n is divergent as well.